So students, in today's lecture number 7, we will be going through the analysis of bars of composite section. So composite section means if any member, any bar is made up of two type of materials, that means they are made up by joining two type of material, and those material having different type of properties, that means they have different type of modulus of elasticity. And when that type of composite section is subjected to loads, whether it is compressive or tensile load, then what will be the behavior of the composite section and what will be the stresses developed in the section. So first of all, let us understand what is the meaning of bar of a composite section. So we can say a composite section may consist of two or more number of material which are joined in such a way that they behave as a single unit. A system which is made up of two or more bars of equal length but of different material subjected to force such that there is same extension or contraction. So that means if you have a bar, a composite section, and it may be hollow section or it may be a solid section. If it is made up of two type of material, that means one A material and other is B material, and two bars are joined such that equal extension is only allowed. So it is restricted that when we are applying stress or we are applying load, then strain will be restricted, that strain will be same in both of the materials. Now let us see this diagram. What do you see here? There is a bar number 1 and bar number 2. They are of two different material. One may be of copper and other may be of steel. And they are subjected to total load P. Now condition is that this composite section will remain vertical, that means there will not be any inclined type of movement. That means if there will be extension, and that extension will be same in material 1 and material 2. Because if there is uneven extension, no doubt the materials are of different properties, and when a load is applied, they will try to behave differently. But since we have restricted that they will have to act as a composite section, so that means whatever will be the extension in 1 and same extension will be in 2. That means if member 1 has the possibility of more extension than 2, then we will say that both will be sharing the load such that extension should remain same. So in other words, we will say because length of both the members is same and when extension is same, so that means strain will be same in member 1 as well as member 2, but they will share the load according to their property. So that means extension allowed is same, strain is same, and stress may differ, but load carrying capacity, that means if P load is applied, so to make the system in equilibrium, member 1 and member 2 will share load such that total load shared by both member 1 and 2 will be equal to P. So point which we have to keep in mind during analysis, during solving any such type of numerical, first point is deformation per unit length, which is also called as strain, will be equal in all bars. because length of each member bar is same and extension allowed is same. So that means strain will remain same in both the members. Second point is total external force or load. Here P is the load. So total external load on composite section will be equal to the sum of the load carried by each bar taking as individual member. So that means whatever be the load, suppose load P member 1 is sharing load P1 and member 2 is sharing load P2. So that means total load P1 and P2 without any failure will be equal to P which is applied externally. So it is very much clear that both member maybe they are of different nature, different property, but now they will act as a composite section as a single member. Now let us consider P is the total load on the composite bar. So this P is the total load. Now if A1 and A2 are the area of cross section of bar 1 and 2, because there may be diameter, if it is a circular member then there will be some diameter. So A1, A2 are the cross section area of bar 1 and bar 2 respectively. As they are of different material, so E1 and E2 will be Young modulus of bar 1 and bar 2. Let us suppose P1 is the load shared by bar 1 and P2 is the load shared by bar 2. So accordingly sigma 1 will be the stress induced in bar 1 and sigma 2 stress induced in bar 2. And as we have already discussed, because it is a composite section, it has to behave as a composite section, as a one member. So deflection or extension or compression in member 1 will be equal to member 2, that is equal to the total deflection or total extension or compression, whatever may be, which depends on the type of loading, that will be equal. So that means extension in member 1 is equal to extension in member 2, so that extension of composite section is also equal to them. So we can use this formula, that means total load P is equal to P1 plus P2. So we can say, as we know that load is equal to stress into area. So if sigma 1 is the stress in member 1, then sigma 1 into A1 will be load carried by member 1, that is P1, and P2 will be given by sigma 2 A2. So sum of those P1 and P2 will be equal to P. Now as again we are repeating that this is a composite section, sigma that delta 1 is equal to delta 2. Delta 1 is the extension or compression in member 1 and delta 2 is extension in member 2. They are equal. So using the formula, that is this is the formula for delta. Delta is PL upon AE. So if delta 1 is P1, now L is same in both the members. So L we have taken as it is, and P1 L upon A1 E1 will be delta 1. P2 L2 upon A2 E2 will be delta 2. So by using this equation and as per the available information, available data, and the required data, required information, required value, we can calculate easily. So we can use this formula. Basic concept is for a composite member that these 2 points which we have to keep in mind. So this is the how the composite section will behave. So solving 1 and 2 required in whatever with the input available, whatever the data available, you can put here, and what is the required information you want to get from the problem, that you can easily get. Now let us go through one numerical of a composite section. So statement is a composite section as shown in figure, we will draw a figure, is made up of a hollow copper tube. Now there is a hollow copper tube enclosing a steel rod. So that means we are placing a steel rod inside a hollow copper tube. Diameter of steel rod is 30 mm and the external and internal diameter of copper tube are 50 mm and 40 mm respectively. And now on this composite section, an axial pull of 45,000 Newton is applied on this assembly. If the length of copper and steel section is kept 150 mm, we have to determine number 1, the stress in steel rod as well as copper tube, and load carried by steel bar and copper tube. So these are the unknowns which we have to find out with the help of all the information available. So it is given that modulus of elasticity for steel is 2.1 into 10 raised to power 5 Newton per millimeter square, and similarly for copper it is 1.1 into 10 raised to power 5 Newton per millimeter. So we have to find out first of all stresses in steel as well as copper. Second is load carried by steel as well as copper. So this will be the diagram actually. Now this outsider shaded portion, that is a tube which is made up of copper having external diameter 5 cm, that means 50 mm. Internal diameter is given 40 mm, and inside we have put a steel rod, and now they are joined at the bottom, so that means they should act as a single member as a composite section. Length of the composite section is L, and you can see the cross section will look like this. That means this is copper and this one is steel, and this much white portion will be the hollow portion. So when P load is applied on this composite section, then as per methodology, some of the load will be taken care by steel and some of the load will be taken care by copper. So we have to find out the stresses as well as the load taken by these members. Now for solution, first of all we will be calculating the area of steel rod, and standard formula which we have already discussed in the previous lectures. You can, if you find any doubt, you can go through the previous lecture. So area of steel rod after calculation, AS, S for steel, A for area, 706.86 millimeter square, and area of copper tube. How to find out the area of a hollow member? You can refer the previous lectures where we have already calculated. So here area of steel rod we have calculated as well as area of copper tube we have calculated. Axial pull along the axis, because we are applying a pull, that means there will be extension. There will not be compression, there will be extension. So axial pull is given 45,000 Newton. Length of each bar is 150 millimeter. Now first of all we have to calculate what are the stresses in the steel rod and copper tube. So what is the methodology? Let us suppose or consider sigma S as stress in steel and sigma C for stress in copper. Similarly, PS the load carried by steel and PC load carried by copper. As for the composite section, strain in one member will be equal to strain in other member. So here strain in copper will be equal to strain in steel. So you can use this formula, that is strain is stress upon modulus of elasticity, sigma S upon ES is strain in steel, sigma C upon EC is strain in copper. And by putting the available information, available data, we are able to calculate that sigma S is equal to 1.909 sigma C. Now, in continuation to this solution, now total load is given by P, that is equal to PS, load carried by steel as well as copper. So it can be calculated sigma SAS plus sigma C AC. Putting all the data as well as sigma S which we have calculated in the previous slide, we can, after solving, we can get sigma C is coming out to be 21.88 Newton per millimeter square and sigma S is coming out 41.77 Newton per millimeter square. Now, second part is load carried by each bar member. So load is given by stress into area, cross-section area of the member. So PS is sigma S into AS. Sigma S is the stress in the steel and AS is the area of the steel. So after calculation we are getting, it is coming out to be 295 to 5.5 Newton. So that means out of the total load was 45,000 Newton. This much load is taken care by steel, and similarly this much load is taken care by concrete. So one thing you have to keep in mind here, that you will find steel is taking more load as compared to concrete because the strength of steel is quite higher than strength of concrete. So now another numerical problem, that means here we will able to understand in this numerical problem that how this methodology, this concept of composite section is applicable in core civil engineering. That means when you are going to construct any building, you will find there one RCC column will be there. RCC means reinforced cement concrete. So that means cement concrete and reinforcement, they are of different nature, they are having different property. Concrete has different property, steel has different property, and they are combined to form a composite section, and which will be known as RCC. Now we will not say that it is steel or concrete separately, we will say it is a composite section, that is RCC. So how this methodology which we have learned in the previous lecture is applicable in actual civil engineering structures or actual civil engineering problem. Now let us consider a reinforced concrete circular column of 500 millimeter diameter, having 4 number of steel bars of 20 mm diameter is embedded in it as a reinforcement. So this is the cross-section area of the column in which 4 bars of 20 mm dia are inserted. Now what is our question? We have to find out the maximum load which column can carry. So that means how much will be the load carrying capacity of this column, that is RCC column, as a composite member. Here what are the restrictions? If the stress in steel and concrete are not to exceed, that means maximum stress which is allowed in steel is 120 Newton per millimeter square, and maximum stress in concrete is allowed 5 Newton per millimeter square. So that means we have to check whether when this this composite circular column is subjected to loading, so that means that time stress in steel should not exceed 120 and simultaneously stress in concrete should not exceed 5 Newton millimeter square, otherwise the column will fail. So we have to find out here what will be the maximum load which this RCC column as a composite section can take without any failure. And another thing given, modulus of elasticity for steel is 18 times modulus of elasticity of concrete. So it is very much clear that major portion of the load will be taken care by steel and other portion of the load will be taken care by concrete. So first of all, we will be here we have to find out that suppose steel is reaching its maximum stress, that is 120. So when steel reaches 120 Newton per mm square, what will be the stress in the concrete? Because to keep the member, to keep this circular column safe, both concrete as well as steel should remain safe. Because if one member fail, if one material fail, then the whole column will fail. Now data given is diameter is of the column is given 500 millimeter. Sigma S maximum. This is the maximum stress in steel which is allowed. That means stress in steel can't go beyond 120, and maximum stress in concrete is allowed is 5 Newton per millimeter square, and the relation between modulus of elasticity of steel and concrete is already given. So let me remove this so that we can actually understand. Now this will be the actual how a column will look. Actually you will see this type of column. That means this is a concrete column in which 4 number of steel bars are inserted, and if you cut, and you will cut here, then from this section if you see the sectional view, then you will see the diameter of the column 500 mm and 4 number of steel bars which we have inserted. So now let us try the solution. First of all, we will find out area of the circular column. So area of circular column from the diameter is coming out to be 196,350. Now this area is of the composite section. So that means some of the area of this composite section will be taken by steel and the remaining will be by concrete. So area of steel, because 4 number of bars, first of all we will calculating area of 1 bar and multiply it by 4, then you will get 1257 millimeter square. So this is the area of steel. Now what will be the actual area of concrete in this section? Actual area of concrete will be total area of the composite section minus area of steel. So this will be the area of this column which is taken care by concrete. Now we have to calculate what is the maximum load carried by column. Suppose let us assume P is the maximum load carrying capacity of the column. So that means P will be equal to load taken by steel plus load taken by concrete. So P will be PC plus PS. PC means load taken by concrete without any failure, load taken by steel PS without any failure. And this will be the formula that PC is equal to sigma C into AC plus sigma S into AS. So you have to keep in mind always that neither steel should fail or neither concrete should fail. None of them should fail. So to check the stress developed in concrete and steel, whether it is acceptable or not, that means we have to check what is the stress actually coming in concrete as well as steel, whether they are exceeding these limit or not. So using again same composite section theory, strain in steel is equal to strain in concrete. So formula, again same formula which we have discussed in the previous problem also, sigma S upon ES is equal to sigma C upon PC. Now again taking maximum allowed stress in steel, first of all let us assume that this column will be able to carry maximum stress in steel. So that means if the column reaches, that means steel in the column reaches its maximum limit of stress, correspondingly what will be the stress in the concrete? So if steel is stressed to its maximum allowable stress, which is given in the numerical problem, 120 Newton per mm square. So we have to find out that correspondingly what will be the stress in concrete. So then stress in concrete is given by this formula. This is the same formula which we have reorganized from the strain in concrete is equal to strain in steel. So you will find here that when if steel is subject reaching its maximum limit 120, then stress in concrete is 6.67. But allowed stress in concrete is 5 Newton per mm square. So that means it will fail. So maximum stress in concrete allowed is 5 Newton per millimeter square. And so taking sigma c, let us consider concrete is reaching maximum limit, that is 5. Now it is allowed only up to 5 Newton per mm square. We have to find the maximum stress occurring in steel. So now in other way, first of all we have assumed that maximum stress in concrete allowed is 5. Now concrete can reach up to 5 Newton per millimeter square. And when concrete reaches maximum, then what will be the stress occurring in steel? Whether it is beyond 120 or whether it is less than 120. So from this, we are able to find out this. So maximum stress in concrete allowed is 5 Newton per millimeter square. So we can't stress it beyond 5. So let us consider that concrete has reached its maximum stress 5 Newton per mm square. And correspondingly, what will be the maximum stress occurring in steel? So by using this formula, we can easily find out that maximum stress in steel is coming out to be 90 Newton per millimeter square, which is 120, which is allowed. So that means it is very much clear that if concrete is stressed up to 5 Newton per millimeter square and steel up to 90 Newton per millimeter square, our composite section, that is RCC column, will not fail. So from this two type of stresses which a section can take, we will find out what will be the load carrying capacity of the section. So therefore, to find the load carrying capacity of the column without fail depends on the above value of stress in steel and concrete. So by using the formula, now P is the total load carrying capacity of the column, TC is the load carried by concrete without fail, PS is the load carrying by steel without fail. So by putting all the values, we are getting that total load carrying capacity of this RCC column as a composite section is 1088.595 kilonewton. So this is the way how the theory which we are going through in strength of material regarding the composite section is applicable in actual civil engineering structures. In lecture number 8, we will be going through the analysis and of the bars